Welcome back. In today's lecture, we are going to talk about Boussinesq hypothesis. Let's see what we have learned in our last lecture. We can use Reynolds averaging to derive the Reynolds-averaged Navier-Stokes equation, which is written as follows, where tau r is the Reynolds stress, which is equal to negative rho times u prime tensor product u prime. So in Boussinesq hypothesis, this Reynolds stress, which is this, is modeled as Newton's viscous stress, which is equal to T times dou I, where I have written this particular expression in Einstein's notation. Here nu T is the turbulent viscosity, also known as eddy viscosity. K is equal, which is the turbulent kinetic energy, and delta Ij is the Kronecker delta. So there are various models that are based on this particular assumption. So to name a few, number one is zero equation model, then one equation model. An example of this is Spalart-Allmaras model. Then number three is two equation model, which are k-epsilon model, k-omega model, k-epsilon SST model, which is shear stress transport. All these models are based on Boussinesq hypothesis. So therefore we should know that in which kind of scenarios this Boussinesq hypothesis is valid. Let's talk about validity of Boussinesq hypothesis. Number one is it is valid in flows which are wall bounded. For example, pipe flows, boundary layer, and channel flows. Number two is free shear flows like mixing layers, etc. Number three, in flows with moderate gradients. For example, flow over an airfoil. But remember, this particular hypothesis, or all these models which are based on this particular hypothesis, cannot be used in flows where the angle of attack is very high. So we'll see in which kind of flows these models cannot be applied. We can also solve indoor airflow, which are HVAC simulations. So these are indoor, and the buoyancy is mild and turbulence is also not highly anisotropic. Then number five is natural convection. There we assume that the density is constant, although the flow is considered compressible. So here we can solve ventilation problems and electronic cooling with incompressible flows. Now let's talk about the limitations of Boussinesq hypothesis, that in what kind of scenarios we cannot apply these models which are based on Boussinesq hypothesis. If there is anisotropic turbulence, then we cannot use Boussinesq hypothesis. The example of this is rotating or curved flow, like in a bent pipe. Another example is flow with separation and secondary motions. And number two is that this particular hypothesis neglects the nonlinearity present in real turbulent flows. An alternative to these limitations are Reynolds stress model. In this model, for every component of the Reynolds stress, a unique transport equation is written and then they are further modeled. Another type of alternative to Boussinesq hypothesis is nonlinear eddy viscosity model. So this particular model extends the Boussinesq hypothesis to include higher order tensor terms. That's it for this particular lecture. We'll continue in our next lecture. Thank you.